what I want to do is to start the issue of quantization of electromagnetic fields. So just as I start this, I would like to discuss one interesting example of a system which is not a classical harmonic oscillator, but which whose equations look like harmonic oscillator equations, and hence I can quantize it. Because when I quantize electromagnetic fields, the way I will approach is I will calculate the total energy of the electromagnetic fields in terms of electric and magnetic fields, and then show that the total energy can be written as a sum of an infinite number of terms. Each one of those terms looks like the energy of a harmonic oscillator. It looks like p square by 2m plus half m omega square x square, where x is something, p is something, need not necessarily be position and momentum, but two conjugate variables. And the moment I put the Hamiltonian in that form, immediately I can use the same principles as I have used for harmonic oscillators by writing x comma p operators is equal to IH cross and then quantize it. So the quantization essentially implies I put this commutation relation, and then I assume that all observables are operators, the system is described by a ket, and then I can solve the problem. So before I do that, for electromagnetic fields, I want to discuss a classical problem where I can use a similar procedure and quantize the problem, and that is an LC circuit. So we all know that this LC circuit behaves like an oscillator. And if you calculate the current in the circuit or the charge on the capacitor, it varies sinusoidally. And if I assume no resistance in the circuit, this will oscillate forever, just like a harmonic oscillator, an undamped harmonic oscillator. What is the frequency of oscillation? Omega 0 is equal to 1 by square root of L times C. Now first I want to write the classical equation and put that classical equation in a form which looks like a harmonic oscillator equation, and then I can quantize the LC circuit. So what is the energy of this energy contained in the LC circuit? The energy is present in the inductance in the form of current variation and also charges on the capacitor. So what is the energy? Half Li square plus, if I write in terms of charge, now let me define a quantity P, which is L dq by dt, Li. So this the Hamiltonian or the energy is simply p square by 2L plus q square by 2C. Please remember, in a harmonic oscillator, the energy is half m omega square x square plus half m. But when I wrote the Hamiltonian, I wrote it as half m omega square x square plus p square by 2m, because x and p are conjugate variables. They satisfy the Hamilton's equations, which are the classical equations. So similarly, I define a quantity p, which is L dq by dt, and I will show you that p and q are conjugate variables, which means that if this is the Hamiltonian of the system, and if I write the Hamilton's equations of motion for this system, they will satisfy the classical equations. Okay, now to make it more apparent, let me define a quantity m which is equal to L. This will correspond to the mass of the corresponding harmonic oscillator. So what about 1 by C? 1 by C becomes L omega naught square, which is equal to m omega naught square. M is nothing but the inductance here. So substituting the value of m And 1 by c here, the Hamiltonian simply becomes p square by 2m plus half m omega naught square q square. It's very similar to the harmonic oscillator. Now, let me just check whether p and q correspond to conjugate variables. So, I need to calculate the if this is Hamiltonian and p and q are conjugate variables, then you know that dq by dt must be equal to del h by del p. This is one of the Hamilton's equations, and the other equation is dp by dt is equal to minus del h by del q. So, what is del h by del p? It is p by m. If I differentiate del h by del p, it becomes p by m. And remember, p is L times I and m is L. So, this is equal to I, which is true. I is dq by dt, q is the charge. And the second equation implies d times Li by dt is equal to minus, let me use this equation, this h for q square by 2c, so it becomes minus q by c. So, this implies L d square q by dt square is equal to minus q by c, which implies d square q by dt square is equal to minus 1 by LC times q, which is nothing but the equation for the charge variation in the LC circuit. Because this will give you a solution, q of time is equal to q0 exponential cos omega naught t and sin omega naught t solutions. So, this taking q as one variable and p as the conjugate variable, where p is Li, which is L dq by dt. Just like in the other harmonic oscillator, p was m dx by dt. So, here it is m is L and dx by dt is dq by dt. So, position in the harmonic oscillator is replaced by charge here, and the velocity or momentum is replaced by L di by dq by dt. Okay. So, this tells me that this is the correct form of Hamiltonian of this LC oscillator. And so, now to quantize this, what I do is I now assume that H is an operator and given by p square by 2m plus half m omega naught square q square, which is actually, I can write it in terms of which is also p square by 2l plus and to quantize, I say that q and p satisfy this commutation relation. This is the crucial point where I am quantizing the LC oscillator. By saying that q and p satisfy this commutation relation, I have transformed the problem from classical to quantum. And the Hamiltonian of the system is given by p square by 2l plus q square by 2c.
This expression for the commutator, this we are saying as per the comparison of this equation with the.
Yes, if I assume q as a variable and p as a conjugate variable, which is what I have shown you, that because that satisfies the Hamilton's equations, which are consistent with the classical equations satisfied by my LC circuit, p and q are conjugate variables and q comma p operators equal to h cross. That is now the quantization. I have quantized the LC circuit by putting this condition. So, first what I have done is I have written the Hamiltonian in terms in the form of a harmonic oscillator problem, and then I quantize. So, what will I get? I can use the same, exactly the same principles as I have done for harmonic oscillator, and I will find energy eigenstates. I can find the eigenstates of the harmonic of the Hamiltonian operator, and I will find that, for example, H will be H cross omega naught A dagger A plus half, where A will be defined as 1 by under root 2 H cross omega naught L into L omega naught Q plus IP. Remember, 1 by 2 m H cross omega naught m omega Q plus IP. This is what I did for harmonic oscillator. M is replaced by L, and Q and P are not now position and momentum. It is some other variable. It's a variable corresponding to my LC circuit. And similarly, I can calculate from here A dagger. Yeah.
So over here we are doing this analysis. Let's say if we have a system which we do not know that it is a the harmonic oscillator or not. So for solving that, I mean, how will we approach the problem? Over here you are saying that we can take the charge as one variable and its conjugate variable is this quantity Li. So how will we get to know in the first place that they will be conjugate variables? I mean,
the first problem is to find out what is the Hamiltonian of the system.
Yeah. Fine.
In terms of pairs of conjugate variables,
So,
right?
How will we know that which is the conjugate?
So I have to write a form of Hamiltonian, calculate the Hamilton's equations of motion, and check whether they are consistent with the classical equations. For example, if you go back to the standard harmonic oscillator problem, and if you write the Hamiltonian as half m omega square x square plus half m v square, and assume that x and v are conjugate variables, and you calculate the Hamilton's equations, they will not be correct equations. They will be inconsistent with the original classical harmonic oscillator equation. So V is not the conjugate variable to X, it is P. Because if you calculate del H by del Q is equal to dQ by dt is equal to del H by del P and the other Hamilton's equation, these equations have to be consistent with the actual dynamical equations of the system. So I think Hamiltonian calculation of the Hamiltonian is not a trivial problem in more complex situations. But I need to form a Hamiltonian. In fact, one starts with the Lagrangian formulation, write the Lagrangian of the system, then from there define the conjugate momenta, then write the Hamiltonian, then write the Hamilton's equations of motion, and then quantize it. That is the standard procedure for a general problem. But here I am looking at a simplified problem because the problem which I am tackling is like a harmonic oscillator.
Yeah. So, for example, if we have some other problem in which we know that the variation is as per the harmonic oscillator, we know beforehand. Now, if we need to formulate in terms of this quantum mechanical analysis, so how will we proceed to find the conjugate variables? Basically, that's the question I'm asking. So, do we have to follow all the procedure?
I think so. I don't think it is just straightforward to write.
This is fine that you are telling that this is the conjugate variable. We are saying that okay, fine.
Because I've shown you by substituting into the Hamilton's equations, I've shown you that it's consistent with the classical equations.
But if we are
I follow. In general, what do? I think in general I have to try out different forms of Hamiltonian and calculate which are the corresponding conjugate variables. There may be a standard procedure for this, but it is not obvious, I think. One has to find out the pairs of conjugate variables and then impose the commutation condition on those conjugate variables, and which will then quantize the problem immediately. So in general, I am not discussing here because finally our electromagnetic field also will be written as a harmonic oscillator. And harmonic oscillator has very nice solutions. Yeah.
Sir, how do we come to know that the commutator between P and Q is going to be I?
See, remember when I did harmonic oscillator, in the harmonic oscillator problem, the commutator between Q and P, the Poisson bracket between Q and P is 1. I showed you that day. X and P. Q is the position, X and P is 1. Because del X by del X into del H by del P by del P minus this thing. So there is a definition of Poisson bracket. So Poisson bracket is equal to 1, XP. I say that the value of Poisson bracket remains the same numerically, and I replace the Poisson bracket by 1 by H cross commutator bracket And that is the quantization now. I can't derive this because quantum mechanics is much broader than classical mechanics. I can't derive quantum mechanics from classical mechanics because classical mechanics is a subset of quantum mechanics. So I postulate some postulates, I put some postulates, and using that postulates, I derive the solution to my problem. If my solution is consistent with what I find experimentally, my procedure is correct. I can't derive Schrodinger equation. That was just written by Schrodinger from his own mind. So this particular procedure was proposed by Dirac. If you look at Dirac's book, the quantization means essentially after I write Hamiltonian in terms of the conjugate variables, then I put QP is equal to IH cross. That is quantization now. And if I quantize the problem, and please remember there is a correspondence principle that classical description should be also possible in terms of quantum mechanical, because I see the harmonic oscillator oscillating back and forth. So I should be able to describe that quantum mechanically. Please remember I told you that the oscillator, the mass spring system which is oscillating like this is not in one of the energy eigenstates. Because if it was in one of the energy eigenstates, the expectation value position would be 0. And that's not what it is. I know I'm seeing the particle moving back and forth like this, which means the expectation value of the position of the particles should be oscillating sinusoidally.
So, since the expectation values follow the classical laws,
Yes.
so that is why we say that whatever we observe the position, that is the
Most probable position, which is the expectation value. Yes. Yes. Similarly, when I quantize the electromagnetic field, I will find that the standard, the laser beam which is coming out, the sinusoidally oscillating field which is coming out, is not represented by a energy eigenket. And there I will introduce what are called as coherent states. I can do the same thing for the harmonic oscillator, oscillating particle, but the analysis is the same. So I don't want to do it for the harmonic oscillator problem, but I want to do it in the electromagnetic field problem. Okay, so when I write this condition, I have quantized the problem. And I am assuming that Q and P are operators, H is an operator, and I will describe the system by a kit, which contains all the information that I can have regarding the system.
So in this case, we wrote just this commutator relation as IH cross.
Yeah.
So whenever there are two conjugate variables, we can write their commutator relation as IH cross.
I think so. Two conjugate variables will always satisfy the equation.
value can be different.
No, because if they are conjugate variables, I think it will be IH cross. I would have to verify this, but I think it will be IH cross, two conjugate variables. But in general, I can have a commutator which is not a number like this. It could be another operator. For example, between A and H, for example, the commutator is not a number, it's another operator. Okay, so it's in principle possible, but what I need to do is, in principle, if I calculate the Poisson bracket, whatever the value I get, I replace the Poisson bracket by 1 by IH cross commutator bracket. Right? So, in our case, what I'm doing is, because the Poisson bracket of Q and P, not for this problem, because I have now reduced the problem to an equivalent harmonic oscillator problem. And I exactly borrow all the results of the harmonic oscillator and put it here. I could have actually derived this and continued with all the calculation of eigenstates. Instead of doing the harmonic oscillator, I could have done the LC circuit first. In a quantum mechanics course, you could have done an LC circuit. So these are all the same problem. Mathematically, they are the same problem. Interpretation of Q and P are different here. In harmonic oscillator, it is different. In electromagnetic fields, it is different. Q corresponds to something in the oscillator. Here it corresponds to something else. In the electromagnetic field, it corresponds to some field variable. Okay?
So just for now.
Yeah.
Sir, suppose right now we are not sure that the commutator relation between two conjugate variables will always be IH cross. Then in this case, what is giving us the intuition that this commutator relation will be IH?
Because the Poisson bracket between Q and P is 1. Because the problem is related equivalent to a harmonic oscillator problem.
But we can also say that since the expressions that we have used, they reduce the Hamiltonian to the same expression
As the harmonic
as
oscillator.
the harmonic oscillator, except that x is replaced by q and
Yeah.
so the relation should be arranged.
Because those equations, those Hamilton's equations are much more general than for a classical mechanical system. So that's a much more general formulation. And I can write the Hamiltonian of a system in terms of two conjugate variables, and those conjugate variables will satisfy this commutation relation immediately. Because the corresponding harmonic oscillator, the corresponding particle harmonic oscillator satisfies these equations, and this problem is exactly equivalent to a harmonic oscillator problem. So I can invert this equation to calculate Q and P, and the energy of this oscillator, energy states of the oscillator will be En is equal to h cross omega naught n plus half, where n is equal to 0, 1, 2. And you can describe the what are called as the number kets. This is a state of the system of the LC circuit in which the energy corresponds to into n plus r. So you see, this tells me that the energy of the LC circuit is quantized. Now let me calculate what is the quantum of energy in this, which means what this means is that LC circuit can have only energies which are differenced by h cross omega naught. Half h cross omega naught, 3 by 2 h cross omega naught, 5 by 2 h cross omega naught, etc. So what is the value of h cross omega naught? Let me calculate. What is the value of h cross? H bar, not h. About 1.05 or something. So let me assume 1.05 into 10 to the minus 34. And what is omega naught I assume for an LC circuit typically? This is nu omega naught, not nu naught. Okay, this is not this Hertz frequency, this is the radians per second frequency. So what is the value? 2 pi times. What is the oscillation frequency of a typical LC circuit in the lab? Is it in hertz, kilohertz, megahertz, terahertz? What is the value of capacitance you take typically? Can you estimate? Picofarads and inductance? Millihenry. So what is the frequency? Can you calculate? Omega naught, 1 by root LC. What is the value? 10 power 6, yes, about 2 pi 10 power 6, yes. What megahertz? So what is this value? This is about 6 times 10 to the minus. This is hardly measurable by you. 10 to the minus 28 joules. So for your classical system, when you look at the LC circuit, it will have almost continuous energy values. Because the difference between the two energy states is so little, you cannot measure the difference. You will not be able to observe. But it is quantized. Just like the harmonic oscillator, if you take the LC circuit in one state, some state for example, so also note that the lowest possible state is the vacuum state, called the vacuum state, in which n is equal to 0. So this is the lowest energy state. The energy is half h cross omega naught. This again comes from the uncertainty principle, because I have put this commutator relation between Q and P. Q and P have a commutation relation, the charge and the current in the circuit. So I can actually, that means what it means is that you cannot have an LC circuit in which there is no current flowing. There's always fluctuation current, there's a fluctuating current, there are fluctuating charges on the capacitor plates continuously. And those fluctuations, there is a minimum amount of fluctuations, and that is determined by quantum mechanics. Of course, for this problem, for the LC circuit, because omega is so small, the classical description is perfectly fine. Just like for a pendulum, classical description is perfectly fine. You need to use quantum mechanics for that. For light, again, you will find the same kind of frequency difference. This is 10 to the power 14 now. So that becomes about 10 to the minus 19 joules. That is the typical energy of a photon. Okay, so this I will say that if your state is in this system, it is in the nth excited state. Just like for atoms, you have different energy levels. Here also there is a sequence of energy levels starting from half h cross omega naught, 3 by h cross omega naught, 5 by h cross omega naught. There's a ladder, complete ladder, up to infinity. There are an infinite number of modes here. So what I've tried to show here is simply the fact that for an LC circuit, I can write a Hamiltonian in terms of pairs of conjugate variables, and when I quantize, I put QP is equal to IH cross. And then I employ my procedure, and that means I have quantized the LC circuit. And I can calculate, for example, I leave it here to calculate what is the current, fluctuating current in the LC circuit when the LC circuit is in the lowest energy state. How will I calculate? All you need to do is you need to calculate delta P. P square average minus P average square. Because P is related to current. P is L times I. So expectation value of P in the state will be 0. Remember, the harmonic oscillator. Expectation value of P square will be finite. So I will get some value for this, and this is nothing but L times delta I. So I can calculate delta I from here, and you will get typical values of about 10 to the minus 13 amperes or something like that. 0.1 picoamperes of current, which is for this kind of oscillator, 1 megahertz oscillator, you will have that current fluctuation will continuously be there all the time. You can't get rid of that fluctuation. It's a quantum fluctuation. Okay, so my objective to do this problem was to sort of show you that if you are given a system and if you can reduce the problem, harmonic oscillator problem, to the Hamiltonian of the problem to a Hamiltonian which looks like a harmonic oscillator Hamiltonian, then I can use all the calculations of the harmonic oscillator problem to do this and to calculate what are the energy eigenstates, what are the expectation values, how does this system behave dynamically, etc., etc. Everything I can calculate. Okay, now, so what I want to do now is, so I'm going to use a similar procedure for electromagnetic fields. So for electromagnetic fields, I will have to calculate the total energy of the electromagnetic waves, and I will show you that the energy of the electromagnetic waves can be written as a sum, an infinite sum of terms which look like harmonic oscillator terms. And so I will show you that the electromagnetic wave consists of an infinite number of independent harmonic oscillators. Each harmonic oscillator corresponds to one particular frequency. Okay, so we need to start from classical Maxwell's equations, and we will do this quantization in free space. Okay, so what are the Maxwell's equations in free space? Divergence E is equal to 0, then divergence B is equal to 0, curl E is equal to minus del B by del T, and curl H is equal to epsilon 0, free space, no charges, no free currents, no free charges. It is del D by del T, D is epsilon 0 E in free space. Okay, this equation, divergence B is equal to 0, tells me B can be written as, in fact, that is a very general equation, whether it is materials or no material, free space, etc. And what is A called? The vector potential. So if I substitute this into the third equation, I get del cross E is equal to minus del by del T of del cross A, so del cross, so this time tells me del cross E plus del A by del T is equal to 0. So what does this imply? E plus del A by del T must be gradient of a scalar. So E must be equal to minus del A by del T plus gradient of a scalar function. I can substitute this into the first equation and I will get del square phi minus del by del T of divergence A is equal to 0. If I substitute this electric field expression in the first equation, I will get del square phi minus del by del T of divergence A is equal to 0. Now, please note that there is a bit of flexibility in my defining the vector potential, because if I add the scalar of any function to A, B will remain the same. The magnetic field does not change by replacing A by A plus gradient of some function chi, for example. So if I replace A by A prime is equal to A plus gradient of some chi, then B is still given by del cross A prime is equal to del cross A. B does not change by redefining the vector potential. So I have a choice in defining the vector potential. So the way I will choose is to make divergence A is equal to 0. I will choose, suppose the A which I get does not satisfy divergence A is equal to 0, I will add the gradient of some scalar function to make sure that the final vector potential that I get satisfies this condition, divergence A is equal to 0. And this is called the Coulomb gauge. And if divergence A is 0, del square phi satisfies this equation, and I also choose phi is equal to 0. That means phi is determined primarily by static charges. That's a constant field at the background, and I just choose the origin. I mean, I just choose the scalar potential as 0 everywhere.
Can you please explain this?
Because of a arbitrariness in defining the vector potential, I will define my vector potential such that divergence A is equal to 0. Suppose you give me an A which does not satisfy divergence A is equal to 0. I will add the gradient of a scalar function to the given A value so that the new A which I get satisfies divergence A is equal to 0. And if divergence A is equal to 0, del square phi is 0, and I choose the solution phi is equal to 0 as, that means the background there is no electrostatic potential. So what I get is, this is called Coulomb gauge. There are other gauges which people use. There's another gauge called the Lorentz gauge, where the condition satisfied by A is different, and this is used in quantum electrodynamics. Okay, so what I get now is that because phi is equal to 0, the electric field is given by minus del A by del T, and the magnetic field is given by H is equal to 1 by mu naught del cross A. So if I get the value of vector potential A, I can find out both the electric field and the magnetic field. So what is the equation satisfied by A? I substitute into the fourth equation now the value for H and the value for E. So H is 1 by mu naught curl A and E is minus del I by del T. So I will get curl of A with 1 by mu naught is equal to epsilon 0 del by del T of minus del A by del T. This implies that gradient of divergence A minus del square A is equal to minus epsilon mu 0 del square A by del T square. And divergence A has been chosen to be 0. So this tells me the equation satisfied by A which is the wave equation. Three-dimensional wave equation satisfied by the vector potential A. So if I solve this equation and get the value of A, I can calculate the corresponding electric field and the magnetic field from these equations. So instead of solving the electric and magnetic fields, I've reduced the problem to solving the problem for vector potential. And calculating the vector potential for a given problem, I can immediately calculate the electric and magnetic fields. So how do I solve this equation? Separation variables technique, for example. So I can write the vector potential is actually a function of position and time. Yeah.
Does the vector potential also vary as the electric magnetic field? I mean, because it satisfies the same wave equation.
Yeah.
So
exactly, because A will have a time and space variation, which will give me corresponding electric field and the magnetic fields. We will solve this equation, calculate the vector potential, and then use these equations to calculate the electric and magnetic fields in terms of the solution of the vector potential. So I can write this as some function of r times some function of time. Let me write this q of t. So this equation becomes del square A into q of t is equal to epsilon 0 mu 0 r Okay, so this is essentially, so let me write, for example, one of the Cartesian components of this A vector. So I will have del square Ax of r into q of t is equal to epsilon 0 mu 0, which is 1 by c square, Ax of r so this tells me 1 by Ax of r del square Ax of r. Now let me take the c square here. C square times this thing is equal to 1 by q of t So this is one of the Cartesian components of the vector potential satisfies this equation, and which I separate into a space dependent part on one side and a time dependent part on the other side. So the space and time dependencies have separated out, and because this equation has to be valid for all space points and all times, this must be equal to a constant, and that constant I choose as minus omega square. Minus omega square, so that the time variation is harmonic and not exponentially amplifying and decreasing. So the solution for q of t, immediately I get exponential I omega minus I omega t and exponential I omega t. Two types of solutions. Okay. So Ax of r vector will now satisfy an equation which I can write from the first this term and equal to minus omega square. And what do I get? I get del square of Ax of r is equal to minus omega square by c square How do I solve this equation? For example, again I can choose separation of variables technique. Write this as a product of an x dependence, y dependence and a z dependence. And what is the kind of solutions I will get? Plane wave solutions, for example. So what will be the solution like? Where k vector is equal to x cap kx plus y cap ky plus z cap kz, and r vector is the position vector x cap x plus y cap y plus z cap z. And k dot k is equal to kx square plus ky square plus kz square must be equal to how much? If you substitute this solution into this equation, I will get minus kx square minus ky square minus kz square is equal to minus omega square by c square, which is essentially the propagation constant of the wave. So that's known. This is the frequency of the wave, that's the propagation constant of the wave. And this is the wave. This solution is a wave corresponding to a wave propagating in some direction defined by the k vector with components kx, ky, kz. So time dependence is of the form exponential plus I omega t or minus I omega t, and the space dependence is of this form. It's completely classical. I'm not doing any quantum right now. It's a completely classical solution. Now, I need to consider an infinite space. The problem in infinite space is all omegas are allowed. Continuous spectrum of omega. I can have any frequency of the electromagnetic field. So, when I continue with the problem to calculate, so what is happening is the electromagnetic field consists of all frequencies that are possible from omega is equal to 0 to infinity. Corresponding k vector magnitude is omega by c, right? Each solution corresponds to, for example, if I multiply this time dependence and the space dependence, what does it give me? Something like exponential I k dot r minus omega t. What is that? What kind of wave is this? It's a plane wave. Exponential I k dot r minus omega t is a plane wave going along the direction defined by the k vector. Similarly, exponential I k dot r plus omega t gives me a wave going in the minus k direction. So these give me solutions corresponding to, and because of these arbitrary values of kx, ky, kz, the only condition is this must be satisfied. So these correspond to all kinds of plane waves going in all directions and having an arbitrary frequency. These are all the independent modes of propagation in free space. Which means if you take a plane wave going like this at a certain frequency, it will propagate unchanged. If you take another plane wave going in this direction, it will go unchanged. It will not get coupled to the other one. These are independent solutions. So the total solution will be written as an integral of all the possible frequencies with all the possible directions of propagation. Now, this makes the problem a little more complex to analyze. So there are methods to simplify the problem, and one of them uses what is called as box normalization. Now, I don't know whether you have done lattice vibrations or phonon spectrum, etc. So for example, what I will do is, I will assume a finite volume of space, a cubic volume of space of side L, so L by L by L, okay? And I will impose the following condition called the periodic boundary condition, which means I will say that the field on this plane x is equal to 0 must be equal to the field on the plane x is equal to L. The field on the plane y is equal to 0 must be equal to the field on the plane y is equal to L. The field on the plane z is equal to 0 must be equal to the field on the plane z is equal to L. So the moment I put this condition, I will discretize the frequencies. Because I have to satisfy the boundary condition that the field here and field here must be the same, I will find that not all values of kx are allowed. For example, if this value of this should be the same at x is equal to 0 and x is equal to L, I can show you that kx must be an integral multiple of 2 pi by L. So what will happen is, I will discretize the frequency spectrum, and instead of working with integrals, I can work with sums. And then, of course, I can let L tend to infinity. Because actually there are no boundaries in free space. So I start with a boundary condition, employ a boundary condition to get the solutions in terms of discretized set of modes instead of a continuous set of modes. And once I get a discrete set of modes, I will solve the problem, and later on, finally the solution to the problem must be independent of the volume, unless I actually take a cavity. See, there are people who work with electromagnetic fields within cavities, Fabry-Perot cavity. There is an actual cavity, and that actual cavity will only support a discrete frequency spectrum. Then there is no problem. But if I am looking at free space, wave is coming and hitting a beam splitter, getting reflected, etc., then I have to worry about the fact that I am using free space propagation. And so I will use this procedure in the next class. What we will do is, we will apply boundary conditions, periodic boundary conditions, and get the solutions in terms of propagating waves. So once I get the solution for A vector, I will get the solution for E vector and H vector. And the energy of the electromagnetic field is, the energy density is half epsilon 0 E dot E plus half mu 0 H dot H. So we will substitute that, calculate the total Hamiltonian, and finally put the Hamiltonian in terms of a sum of terms which look like harmonic oscillator terms, which look like p square by 2m plus half m omega square x square. Okay, so and then the quantization becomes obvious. So we'll stop here.